Hello, thank you very much for watching this recording for SSBSE 2022 in Singapore. My name is Kenneth Chan, and this work is done in collaboration with my advisor, Dr. Betty Chen. Today, I'm going to be presenting my work on EvoAttack, which is an evolutionary search-based approach to generate adversarial examples against object detection models. So recent success in deep learning, specifically deep neural networks, have really promoted their use in real-world applications. For example, we've seen their surge in usage in smart grid systems, medical imaging, and autonomous vehicles. In medical imaging, we might take, say, an X-ray of a patient's chest and predict if there's a certain medical condition that exists in that image. For example, here we have some examples of chest X-rays and the corresponding label of no findings and some medical conditions. In autonomous vehicles, we might take pictures of the road seen around us and identify objects of interest, such as vehicles, pedestrians, or cyclists, in order for us to decide how we should move a vehicle accordingly. Now, in safety-critical applications, the failure of these systems may lead to dangerous outcomes, such as financial damages, injuries, and even loss of life. For example, we can think if autonomous vehicles, if these networks fails to detect pedestrian, we might lead to collisions. And indeed, we do see some potential impact that has already happened with these neural networks. Specifically, in 2016, Tesla's autopilot failed to recognize a white trailer for a truck against a bright background, which resulted in the Tesla driving directly into the trailer, killing the driver. In the same year, Google's self-driving car was involved in its first accident when it assumed that a bus would yield during a lane merge. However, the bus did not yield, and it led to a collision between the autonomous vehicle and the bus. Fortunately, in this accident, there was no human injuries. In last year alone, Tesla Autopilot has been involved in 273 reported crashes. And here we see a scene of a Tesla that crashed in 2018 into an emergency vehicle, which prompted some investigations. So in this work, we're proposing a technique that allows us to generate adversarial examples for object detection system in order for us to enable system testing and analysis. Specifically, we focus on three different parts of our attack. First, it is black box, meaning that we do not need access to the underlying weights and gradients of the model to be attacked. Second, it is model agnostic, which means that we're not concerned with what type of architecture that the model is. And finally, it is data agnostic, which means that we can use any data set that is object detection based. Now that we've talked a bit about the potential impacts of deep neural networks, let's describe what they are. DNNs are artificial neural networks that consist of three layers. Specifically, we have an input layer, which is, for example, in the medical imaging example, we might map each pixel of the image into an input neuron. Next, we have a series of these hidden layers of units, hence leading to the term deep learning. In a real system, we may have millions, if not billions, of these nodes that are connected, such that when we pass in the input of our image, these nodes will apply mathematical operations in order to abstract these abstract complex features directly from the training data. And then finally, we have our output layer. In our example of the medical imaging, this might be the presence of a condition or not, and maybe what type of condition is present in the image. So these DNNs currently face several issues. For example, they are susceptible to overfitting. First, overfitting is essentially where we have trained our model and it performs very well with training data. However, when we deploy the model into a real-world situation, it fails to generalize well into that data set. So it fails to perform well for data that it has not seen before. Additionally, they are susceptible to inputs with small but expected deviations, such as minor lighting changes, contrast, and environmental conditions such as rain, fog, and so on. And finally, the focus of this paper, we're focused on malicious perturbation, where an adversary generates some malicious perturbation in order to prevent correct model detection or prediction for image classifications. So that's basically what adversarial examples are. They're carefully crafted inputs with malicious human imperceptible perturbation. So at the bottom here, we see on the left is a scene of image taken from the Waymo open dataset, where we see a urban street with cars parked on the side of the road. Our model correctly identified vehicles that are parked along the side of the road and drew bounding boxes around them. However, when we add this perturbation noise filter here, multiplied by a scale of 10 here, just to show the visibility, we end up with these adversarial examples where our model now fails to completely detect any of these vehicles. And as we can notice, for us as humans, these perturbation is imperceptible. So when we look at this image, we can't really tell any difference, and we can still correctly identify cars. However, our object detection model now can no longer detect these vehicles. There are two key classification categories that we classify adversarial examples into. It is white box attacks and black box attacks. In a white box attack, the adversary has complete access and any kind of assumption about the model to be attacked. They have access to sensitive information such as the weights, architecture, and gradients of the information. In a black box attack, this is a bit more of a tighter adversarial assumption. The adversary only has access to a compiled model of the DNN. What they can do is they can query this model with any kind of input that they want and obtain the label of the model. This is much similar to how attacks might be launched in real-world scenarios where the adversary might be able to buy, say, a Tesla car to obtain the DNN on top of built into the vehicle. However, they cannot analyze the DNN in order to obtain, say, gradients and other weights in order to launch a white box attack onto the system. And for particularly when we talk about computer vision, this paper really concerns with object detection. And this slide here describes the difference between image classification and object detection. In the problem of image classification, we're concerned with labeling one object in an image with a correct label. So for example, if I provide the computer vision algorithm with an image of a cat, the algorithm should correctly predict that it is a cat. In object detection, we're instead interested in being able to detect up to n number of objects in these images. We would like to draw bounding boxes around these objects correspondingly, and then also label give their probabilities of the labels. For the adversary, their assumption is also different. In image classification, we're interested in simply changing the label into an incorrect one. So we simply have to change the probability of an incorrect label such that it is greater than the correct label. In object recognition, we would like to prevent the detection of all objects in that image. Existing research have addressed mostly image classification. Szekely et al., Goodfellow et al., Carney and Wagler have really pioneered the work of adversarial examples, but they focus on image classification and white box attack. These attack analyzes the gradient information of the model and introduce perturbation that will most likely lead to mispredictions. Since then, a number of researchers have explored black box and or evolutionary search-based attacks for image classification. In the recent years, we have seen a number of research that addresses object detection algorithms. However, they use white box attack, again, analyzing the gradient information in order to generate adversarial example. In our work, we really focus on this area that has largely been unexplored, that is black box techniques for object detection algorithms. This slide introduces the methodology of our approach. Our objective for the model is to prevent the model to be able to detect objects in these images. So we take in an input, the model, and some clean input images sampled from the dataset. These don't have to originate from the dataset. However, we use images that are selected from the dataset to demonstrate the effectiveness of our approach. So we use a generational genetic algorithm in order to promote these individuals in these images to evolve into adversarial examples, right? And our perturbation is largely driven by mutation. Below here, we show an example of what our pipeline would look like. First, we put in an image of a correct image. So this is a clean image where our model now correctly detects 4 vehicles. And once we pass it through our black box attack method, we generate an adversarial examples. Now that with this one, our model failed to predict the vehicles similar to the clean input, unlike the clean input. This data flow diagram shows how EvoAttack uses evolutionary search in order to generate adversarial examples. First, we obtain an image from the dataset. We map this image to a solution space. In our work, we mapped each image into a 3D matrix that is for the ij pixel in the image is directly mapped to the ij element in the matrix. Once we've initialized a population, we go through our typical generational GA process where we use tournament selection and point crossover in order to select parents. Once the parents have been selected, each individual has a chance to go through mutation. In the next couple slides, we'll describe the mutation schemes in greater details. Once the individual has been mutated, we calculate their fitness using the black box object detection model. Again, we do not need access to the hidden sensitive information of the model. We simply need to use the model to predict the output label of our current population. Once we predicted the population, we sort the individuals, and if an adversarial example has been found, we terminate our algorithm and return the adversarial example. If not, we return the population back to tournament selection and crossover to iteratively essentially add perturbation into these images until an adversarial example has been found. So EvoAttack uses several key insights in order to minimize our perturbation. First, we created a different fitness score that allows us to dynamically adjust based on the number of detected objects. In traditional image classification attacks, we simply use the correct confidence score, the correct label's confidence score as our fitness score. Essentially, we're trying to minimize this such that an incorrect label will be greater than that of the correct label. However, in object detection, because we have up to n number of objects, we needed to develop a new fitness score for that. And essentially what we're using here is the sum of each of these detected objects' confidence score. And by using that, we promote perturbations that will iteratively reduce this each of the confidence score that's been detected in the image. Additionally, we have the advantage that when we successfully have removed one object from the adversarial example, this fitness score will adjust itself dynamically to remove that element from the fitness score. Our second key insight allows us to identify regions of interest to localize our perturbation. Specifically, in image classification, because we use the entire image's input to obtain a label, just one label, each pixel in that image may have a chance to influence the outputs of the prediction. However, in object detection, because most of that image might be of a background, they might not directly contribute to the output of the model. As a result, we needed to develop a technique that enables us to localize the perturbations such that we're not perturbing pixels that do not directly contribute to the output of the model. Specifically, we leverage our previous generation's model evaluation results in order to find pixels in bounding boxes that we would like to modify. Additionally, we introduced a adaptive mutation scheme in order to minimize the perturbation. Traditional approaches in image classification techniques modify each pixel of an image with a p mutation probability. However, we find that when we apply this technique to object detection algorithm, it quickly changes a lot of pixels that might not be necessary in order for us to attack these images. So we introduced this new formula that starts with very little amounts of perturbations and scales this perturbation dynamically up as the number of generation increases. After a specific threshold number of generation, we switch to a more aggressive search approach in order to promote convergence. In this equation here, alpha, beta, and p-mutes are hyperparameters that we set in order to optimize either the number of perturbation or the computational time. For our validation work, we implemented some object detection algorithms using the PyTorch learning platform. Our dataset that we use is the Microsoft Coco dataset and the Waymo Open datasets. We use two models, the RetinaNet and the faster RCNN networks. We fine-tuned our parameters based on existing state-of-the-art image classification attacks, and we have fine-tuned them to our object detection attacks. Each experiment generates 30 adversarial examples that are randomly sampled from the testing datasets. In our first experiment, we demonstrate that our adaptive mutation operator and evolutionary search in general does actually work. We applied our attack to a retina net trained over the Microsoft COCO dataset. In this table, this first section here shows our average statistics for the input. So over the 30 images, we see there's an average 2.7 objects that we detected in the images. And there's about 114,000 on average number of pixels that are in bounding boxes. When we applied random search, EvoAttack using traditional mutates, so each pixel has a p-mutate chance to mutate, and EvoAttack adapts mutation, we see that random search performs extremely poorly in terms of the number of pixels, the percentage of pixel change, and the degree of perturbation. Now, when we apply evolutionary search, so in EvoAttack using traditional mutates, we see that we only have to change about 50% of the pixels that are in the bounding boxes in order to generate adversarial examples. The reason why random search has greater than 100% is because random search does not localize the perturbation. We're simply changing pixels in the image, a random number of pixels in the image, until an adversarial example is found. Finally, our adaptive mutation scheme introduces even less perturbation. Specifically, we only have to change about a third of our image compared to a fifth of the pixels in bounding boxes in order for us to generate adversarial examples. The columns here to the right shows the adversarial examples that are easy to perturb or require very little perturbation in order for us to attack. In EvoAttack, when we use the adaptive mutation scheme, these images only required about 6% of the pixels in bounding boxes to be modified in order for us to generate adversarial examples. That is to remove all the prediction labels that the algorithm is able to make. Compared to EvoAttack, which over these set of 20 images required about a third of the images to be changed. So in experiment 1, we've demonstrated that we can generate adversarial examples drastically better than random search. The mutation operator is capable of reducing the number of and degree of perturbation compared to traditional search methods. And specifically against RenderNet, we found that 20 out of the 30 images required very small amount of changes in order for us to prevent the model's detection. These two images show some input samples. On the left here, we see a scene at a skateboarding event where our model successfully predicted some persons in this image. The top here shows the adversarial example generated with traditional mutation, while the bottom shows the adversarial example generated with adaptive mutation scheme. We see that the number of pixel that is required to be changed is drastically reduced in adaptive mutation scheme. And the noise filter, again, this is multiplied by a factor of 10 for visibility. We can kind of see some pixelations in the noise filter for the traditional mutation. However, we can barely see any in adaptive mutation. On the right here, we see a scene of a skier. This image is harder to perturb. Adaptive mutation took about 77% of the pixels that needed to be changed in order for us to remove the correct label of person in this image. We still perform better than traditional mutation, which took about 83% of the pixels in bounding boxes to be changed. However, because this image is harder to perturb, this number is much closer. In our second experiment, we demonstrate that EvoAttack is model agnostic. Specifically, we have applied our attack to the faster RCNN mobile net. Once again, we compared our attack with random, EvoAttack using traditional mutation, and EvoAttack using the adaptive mutation scheme. Random search performs extremely poorly as expected, and then EvoAttack and EvoAttack attack shows that evolutionary search does indeed produce adversarial examples that are decently optimal. Specifically, adaptive mutation scheme still performs better than EvoAttack, albeit not by that much. Out of the 30 images, these are the same images that we used for the retina net. Only 6 of those images were easily perturbed by the adaptive mutation scheme. Specifically, now we have an average of 10% of the pixels that are changed compared to about 50% of the pixels that are changed in the bounded boxes. So according to the results for experiment 2, we have showed that EvoAttack is model agnostic. When evaluating the two models, we showed that faster RCNN essentially is more robust against adversarial examples generated by EvoAttack than the retina net because only 6 of the 30 images required very little perturbation. So overall, the number of perturbation in order for us to be able to prevent object detection is much greater than that of retina net. Essentially, this showed that EvoAttack can be used as a testing technique in order for us to evaluate the model's performance, robustness against these perturbations. And finally, in our third experiment, we demonstrate that EvoAttack is data agnostic. We applied EvoAttack to two different data sets. So our previous experiments where we applied it to the Microsoft Cocoa data set, and we've also applied it to the Waymo Open data set, which is an autonomous vehicle data set that consists of image taken atop a camera mounted on a vehicle. So these road scenes are obtained from the Waymo Open data set. As we can see here on our left, our clean inputs, our model is able to successfully detect vehicles, cyclists, and pedestrians in these images. However, when we add this perturbation layer, multiplied by a factor of 10 here for visibility, we have adversarial examples where our model fails to predict these objects of interest. And again, to us as humans, we can't really see these perturbations, and we can still correctly identify each of these vehicles in the image. So we've demonstrated that EvoAttack is data agnostic for experiment 3. Additionally, we have shown that EvoAttack can successfully prevent detection on some real-world data set that can potentially lead to some fatal situations. If we can imagine if we are attacking an autonomous vehicle while it's driving on the road, if we prevent detection of pedestrians, cyclists, or vehicles, you might lead to some fatal accident where we collide with the objects that we would otherwise like to avoid. So because GAs are generated, relies on non-determinism to generate adversarial examples, we randomly sampled a wide variety of images from the testing sets. Over multiple runs of EvoAttack on the same set of images, we found the coefficient of variations for each of the metrics measured are less than 0.15. This means that over multiple runs, we produce very similar types of perturbation in order to prevent detection. For random search, we found that there's a large variance in repeat experiment, and this is largely due to the fact that we're simply using randomness for generating these perturbations. However, we know that the best performing individuals of these repeat experiments are still significantly worse than EvoAttack's adversarial examples. And finally, the images that we have selected to display in the paper and the presentation here is just randomly chosen from our pool of results. We did not apply any selection schemes. In conclusion, we've introduced an evolutionary search-based attack for object detection algorithm, a space that have not really been explored before. Our attack is black box, data, and model agnostic. We've demonstrated the potential impact of these attacks using real-world safety-critical datasets and applications. In future work, we plan on improving the performance, such as computational time and reducing perturbation for the adversarial examples using multi-objective optimization, such as NSGA2 or parallel GAs. We would like to try to identify optimal hyperparameters using specific tuning approaches. And finally, we would like to explore how we can generate a diverse set of adversarial examples that results in different behaviors of our model using novelty search in order to evaluate how adversary example noise can affect our models. And that concludes the presentation for EvoAttack. Thank you very much for listening to the talk and sticking with me towards the end. If you have any question, please feel free to reach out to me or my advisor. Thank you very much.